I did. Yeah, I feel like I'm finally just about adjusted to the jet lag before leaving tomorrow. So I think there is a
yeah. Okay, so thank you everybody for coming for this month's installment of the Chalmers AI for Science seminar series. So today it's our pleasure to introduce Brian Trippe he's an assistant professor at Stanford University. He has done his undergraduate at Columbia College in New York, and then he moved on to do a master's of engineering in University of Cambridge, and he did his PhD under the advisory of Tamara Broderick at MIT, and he's been doing research stints both with David Baker at the University of Washington, and then a postdoc at Columbia with David Bly and Simon Tavare. And since 2024, he's been an assistant professor where he's working on exciting stuff related to generative modeling and proteins. And he has a very diverse background. So he's a very nice sort of exemplary of the kind of people that we want to represent in this seminar. So please welcome, join me in welcoming Brian to the floor, please.
Thanks, Simon, for the kind introduction. Yeah, super happy to be here sharing some of my work today. Yeah, it would be great. Feel free to ask questions as we go through. Love having more interaction. Yeah, so today I'm going to be talking about calibration methods for generative models and some applications specifically to protein structure modeling and design. So to set the stage, yeah, deep generative models have really been transformative in protein structure modeling and design. So one application of this is something that I was involved in my postdoc, is using diffusion models for generating novel binding proteins to like tightly stick to arbitrary protein targets. This is something that has quite immediate therapeutic applications for biologic drug design. And of course, before this, right, it's really, I think, almost impossible to overstate the impact that AlphaFold and related methods have for structural prediction. And in the most sort of recent variants of these methods, yeah, generative modeling and diffusion models are a key part of like sampling the space of possible structures. But yeah, there's some quite significant limitations of these approaches. So with generative models for design, right, we often see quite stark trade-offs between the diversity of generations that we see and the quality of the generations. And on the structure prediction side, yeah, we find these structural prediction models are insensitive to mutations, which is yeah, quite core to much of what we want to get out of them for interpreting like yeah, variations that are causal of disease, as well as when we're trying to refine proteins in design context. So one reason for this is that I think we've really lacked methods that can sufficiently precisely control distributional properties of the generations coming out of these models. And yeah, I'll become more precise about that. But and this is really the subject of the talk today, of how do we incorporate like yeah, distributional constraints into the outputs of these generative models. So as a first concrete example, in the context of protein design, here I'm showing some examples of generations from a diffusion model over protein backbones. This is Genie 2 from Mohammed Al-Qarashi's lab for these samples, which is in many ways, yeah, among several methods is improving on the generations of Rosetta-fold diffusion. But to those who are sort of initiated, you'll notice a strong lack of diversity in these generations where, right, for these six sort of not cherry-picked samples, they're almost entirely alpha helical. To get a sense of how stark this lack of diversity is, right, we can just look at a density plot for, right, each sample. Where does it fall in terms of its composition of helical versus like beta strand composition? So annotating the fraction of residues in each of these secondary structure elements. Yeah, by comparison to yeah, say like natural proteins in the Cath databases, sort of a diverse representative subset, right? We're only capturing this small slice at the bottom right. So the cause for this, I mean, there are a few causes for these sort of phenomena that we see not only in protein structure models, but also more broadly. In this case, the main sort of source is yeah, inference time sampling heuristics. So in fact, to get high quality samples out of these diffusion models, we can typically do this only when we reduce the amount of noise that we add at each step in the diffusion generative process. And that incurs this loss of diversity. But more generally, often we have access to data that's not representative of like the target distributions that we want to sample. Right, that will also incur biases in what we learn, right? Post-training, like fine-tuning, right? Things like, yeah, like DPO preference optimization also can introduce shifts in generative models. Optimization error are all things that can cause statistics of our samples to deviate from what we want them to be. So, and what I'll tell you about today, we frame these issues as an instance of this calibration problem. So to formalize this, right, if we have some base generative model with parameters theta base and some potentially high dimensional statistic that we're going to call H and a target value for its expectation, right, we'd say that this model is calibrated if the expectation under our model of this statistic is equal to H star and miscalibrated otherwise. Then the methodological goal that I'll be talking about is in the case where our base model is miscalibrated, how do we find a new setting of the parameters such that right, with this new setting, we obtain calibration without moving too far away from this base model? Yeah, please. Yeah.
Many such, and then we'll have multiple that you want to be calibrated towards.
Yeah. So I guess you can interpret this H and H as scalar valued or vector valued. In the case of a vector valued statistic. Yeah. So I'll further on in the talk show results calibrating in this case, but there, right, right, we'll be describing this calibration target of these Cath domains with a discretization of the bivariate CDF. So we have many evaluations of indicators of are we sort of
multiple targets you want to calibrate towards?
Yeah, for sure. Yeah. So I guess yeah, I mean, so I guess broadly the farther you need to move to achieve this calibration, yeah, the more difficult the problem will be. And sometimes I think that can be captured by dimensionality. But for instance, in this case, right, when we sort of describe this calibration to this distribution through a discretization of the CDF, as we sort of increase the density of that grid, the sort of effective dimensionality of the constraint doesn't actually increase. So the link there, I think, isn't really super precisely direct. Yeah, it's a good question. Yeah, does this goal make sense? This is another good time to clarify notation if things are unclear. Yeah, so there's been some related work on this problem. Yeah, one sort of related bucket of work are like so-called reward fine-tuning algorithms. So think like DPO, direct preference optimization, in the context of language models or adjoint matching for diffusion generative models. Um, yeah, and these solve this sort of related problem of fine-tuning, but when you have sort of a reward function specified at the level of individual samples rather than like a functional of the sampling distribution that you're trying to fit, right? So it's not immediately clear how you would be able to apply a reward fine-tuning method to sort of achieve this sort of calibration. There's been a little bit of work on distributional constraints, but yeah, I mean, the couple papers that have looked at this have been yeah, developing algorithms that they're quite specific to like individual classes of models, and with typically quite poor empirical performance, so failing to actually reduce the majority of miscalibration error. So this talk is about practical calibration algorithms that can apply to diverse model classes, data types, and constraint types. This is a roadmap for the rest of this talk. Yeah, I'll describe the methods that yeah, we've been developing for this problem. This is work primarily with yeah, two PhD students at Stanford, Henry Smith and Nate Diamond. And then yeah, because I think it's particularly close to the interests of some folks in this group, I'll talk about also some preliminary work in applying these methods to protein ensemble modeling. And the preliminary work here is with two other students at Stanford, Arthur Dang and Jiaying Li. Right. So yeah, first into this framework for calibrating generative models. So yeah, I'm going to set up before, as I introduced it, we have our base model, the statistic, and we want this p theta that will be matching this constraint without being too far from our base model. And yeah, the first step is framing this as a constrained optimization problem. So I mean, for simplicity and because it's will lead to computationally tractable objectives. Yeah, we formalize this notion of closeness as closeness in called Leibler divergence of the model that we're fitting to the base. So in this sort of geometric view, right? I mean, you can view this as right, we have this very large space of all possible distributions where there's right, a subspace of those that meet this constraint. Some subset of these might be right within the class of generative models that we want to train to. And yeah, the one within that class that we're going to look for is the one that's closest, yeah, this KL metric. Yeah.
Asking about dual formulation also. Minimize the error between the calibrations subject to the distribution being close to the base model.
Yeah, yeah. So
the KL divergence constraint could have that formulation.
Yeah, yeah. Yeah, indeed. So I mean, I guess like maybe the first thing to observe about this is that like we can't actually even solve this problem directly as it's stated. In a dual formulation, I'll describe. Yeah, actually on the next slide. Yeah, that can help get around some of these challenges. But yeah, I mean, maybe just to make these explicit. Yeah, I mean, we have this complicated constraint that's like not convex in the parameters that we want to optimize. But not only is it non-convex, but we can't even directly evaluate whether or not we're in this set if we have a complicated generative model that we have access to only through a sampling mechanism. So yeah, I mean, that second piece, right, is satisfaction of this constraint, right, involves computing an intractable expectation. So yeah, first thinking about this first issue of the intractability of the constraint, yeah, we propose two surrogate objectives to soften this constraint. So the first um, is bringing in sort of relaxing the constraint with just a penalty on distance and KL divergence. And then a second approach that I'll have more to say about on the next slide is reformulating this problem as something that we can directly tackle with a reward fine-tuning algorithm, so that it opens up sort of another avenue of algorithmic approaches. And then for this piece of intractable expectations, the next proposal is gradient estimators that are amenable for stochastic optimization, so that we can actually, right, tractably implement this or approaches. And ultimately these algorithms will be something that you can use so long as you can sample from the model in question, as well as compute likelihoods of its generations and gradients of these likelihoods with respect to parameters. Right. So I think this first surrogate objective, this CGM relax method, is pretty straightforward, I guess, in the way of softening the constraint just with the L2 distance of the current state. Yeah.
Wondering about the second requirement. That's, I mean, typically not so straightforward for many of the modern generative models. I like it with the sample. Think about, I guess you will go into that, how or under what conditions you can do this.
Yeah. So I guess I would say for like diffusion models where I think we've been able to get quite compelling empirical results. The likelihood that's intractable is the likelihood of the marginal of the final generated state. But if you think of the generative model as a model over the full paths that are generated, then you can directly compute these likelihoods. So for diffusion models, this is a path. For autoregressive generative models, this is also straightforward and commonly used. I mean, in our paper, we also look at, I won't talk more about I don't have slides talking more about the details, but for masked generative models as well, right, through the same approach of thinking of the state as the full trajectory, you can compute these densities. I think a main, for flow matching models where you stick to deterministic generation is the case where, I mean, the common wisdom, I guess, is that it's easier to compute likelihoods with these compared to diffusion models. But that's not been my experience in practice with just the computational difficulty of training on likelihood. So that I guess falls outside of what we found to be practical. Although actually in our paper we do also have an application to this tar flow flow-based generative model that is different from the continuous ODE models that I know you've been using lately. Yeah.
Why is it satisfactory? So it's straightforward.
Yeah. So they in many cases we've found, I think there's still with deep learning methods, there are many things that I think necessarily end up being problem dependent, right? So in some cases, I think each can outperform the other. In practice, we've been having more success with this CGM relax approach for most problems, but it has a hyperparameter that's more difficult to tune. I mean, I think I don't think either of these methods are enough for everything that we want to solve now. But this CGM reward method, I think, is quite interesting. So we'll talk a bit more about that now. Um, so the way that we get to this is through a connection to the maximum entropy problem from information theory. So this is sort of the non-parametric version of the calibration problem as I stated it, where right, I mean, this is the same initial objective, but I posted just with a different domain. So looking at the optimization over all distributions that are absolutely continuous with respect to the base model, right? So the solution to this might be outside of the class of generative models that we're working with. Um, uh, but yeah, and sort of key step in bringing this towards a practical algorithm is this result that under like pretty mild conditions, yeah, which is one place where high dimensionality actually can end up producing an issue, high dimensionality of the constraint. But under relatively mild conditions, the solution to this non-parametric maximum entropy problem has the form of an exponential tilt on top of the base generative model, where right, this tilt is just going to be right, this log linear term with right, this parameter alpha, the same dimension of the constraint as I'm showing here. And I've quite suggestively chosen to write this as R, because this matches on with what many reward fine-tuning based methods have targeted. But yeah, so this suggests an approach for model fitting in two steps, where we first seek to identify this alpha star, defining this tilt, and then we minimize a divergence to this p alpha star. And yeah, a classic exponential family result tells us that this alpha star that characterizes the max-sense solution is actually the solution to a convex optimization problem of this form. So yeah, here we're now almost at a practical approach for keeping this alpha. The main difficulty being this second term involving another intractable integral over the generative model. But this turns out to be relatively easy to approximate right, by Monte Carlo. So drawing samples from our base model and then replacing that integral with an average against the empirical measure of our samples to get something that we chose a consistent in the number of Monte Carlo samples estimate for alpha star and remains a convex problem that we can immediately solve off the shelf with a convex solver. So we for this use like CVX pi. And then for the second piece, for simplicity and intractability, we again choose this Kohlberg-Leibler divergence for the thing to minimize to our approximation of P alpha star. And together this gets this CGM reward objective that has this form of the KL divergence to our base model plus this expected reward term.
So we are other Bregman divergence, and at least the simplest would take some other Bregman divergence.
Yeah, I think there's nothing too special about KL here. I mean, any Bregman divergence where you only required the target up to normalizing constant would be fine. Right. So again, sort of looking back at this geometric view, right? We can think of this P alpha star on the bottom left as right, the closest thing in KL lying on this constraint set, presumably outside of the class of generative models. and then the solution to this, the optimization problem being the projection of that back onto the model class. So looking at these side by side and comparing, we have different sources of error and different hyperparameters. So right for this like reward objective, the model capacity is a limiting factor. Right, and how close we'll get to the right thing. Or sorry, for the reward method, right? If we had a very large model class, right, it will get arbitrarily close to this P alpha star. But with the relax method, right, for any finite lambda that we choose, like we're due to this constraint relaxing, we're going to be sitting off of this line. Yeah. So these are the hyperparameters. So a less crucial hyperparameter, less crucial in the sense of empirically we see less robustness is the number of Monte Carlo samples that you use. So in practice, you need to choose some n that's large enough.
So asymptotically, they're equivalent, these two things.
Yeah, so in the limit where we send this lambda to 0, and the limit where we send the size of the model class to include everything, then they'll all bring us to this P alpha star. Good. Any other questions about? Okay. Yeah, so the next piece I'll talk about are it's this piece on gradient estimators for stochastic optimization. So here the main trick and tool that we use is like score-based gradient estimation. Or those who maybe see more reinforcement learning papers would see this as policy gradient. But yeah, first it's just motivate what we need to do here and why it's not just immediately straightforward. Is right, we have these objectives that are defined as an expectation over like an expectation that depends on the model class, and we're looking for some g hat gradient estimate whose expected value is equal to the gradient of the objective that we care about. This is sort of the necessary and sufficient condition to expect stochastic optimization to work well. And although Monte Carlo immediately gives us a way to produce unbiased estimates of a loss like this just by sampling, that's not the case for gradients. So we can't push this gradient operator into the expectation directly. So the key idea for score-based gradient estimation in the simplest form, I think is naturally seen through the perspective of like an importance reweighting. So if we think of redefining our objective as depending on not only our parameter theta, but some other parameter theta prime, right? We can rewrite L theta as right this L of theta theta prime for any theta prime that we choose. So then if instead we compute, and quite directly, if we produce a Monte Carlo estimate of this using samples from p theta prime, right, we'll be getting this unbiased estimate of the loss again. And with this formulation, right now the expectation is no longer depending on theta, only on theta prime. So we can push in the gradient operator. We directly get this unbiasedness. And the main insight is that this holds even if I choose this theta prime to be equal to the theta that's the current like setting of the parameters that I'm trying to optimize. Which means that I can do this just carrying one copy of my parameters around and using that for this sampling.
can you give some intuition to this? Because that would be equivalent to the case for, I mean, the reweighing term would basically become one, right?
Yeah. So
Maybe disconnect the calculation, the gradient calculation, and then you arrive at the standard policy gradient.
yeah. So I mean, this is directly the policy gradient. Yeah. So indeed, it takes a little bit more thinking through. So yeah, I mean, I guess many of us, it's easier to think algorithmically, or some of the procedure is, right, you sample many times from the space generative model, right, and we're going to call this ratio of these densities, this importance weight, W theta xm. And yeah, I mean, maybe unintuitively, right, this weight will always be equal to 1 exactly. But when we push this gradient in, right, it's going to have a non-trivial gradient, right? And I guess moving from in this last equality from the right side to the left is maybe easier to see why this is the same thing as the gradient of the log density or the score, which is where the terminology for score-based gradient estimation comes in.
You also thought about other ways of you like designing your P theta prime in such a way that you have lower, like the conversion with lower steps, like having a distribution where you would have a lower variance on the gradient estimate, so you could get away with fewer samples. Is that possible?
Yeah, it's an interesting idea. I mean, I think for yeah, I would say I haven't thought about this. I mean, I think there's a conceptual advantage of trying to develop algorithms for like models that are given to you where you maybe don't have a place in the design. I mean, just with the sort of proliferation of this foundation model paradigm where I think the majority of model training that people do is on top of a pre-trained existing architecture. But I mean, in a setting where you are willing to be designing the base models as well, perhaps the synthesis, I mean, I'm sure that there are.
I guess that will fall into the category of like control variance, but that'll be similar to control variance, sort of things.
Yeah. I mean, I suppose if there's a question like the initial question was, are there certain model classes for which you can better reduce variance?
Yeah.
So I mean, like we certainly, yeah. I mean, so sort of some standard and non-standard control variants that we use. But yeah, I mean, empirically this is important. But I don't have much intuition for how this actually depends on the model class. Yeah. Yeah, I would say so. Yeah, I'm not going to talk more about the details of this now, but yeah, in order to have this work in our setting, particularly for the CGM relax method, yeah, I mean, it was sort of being sly in the first line here, right, this violation penalty is not something that we can just write as the expectation of some f of x theta over single samples. Right, so roughly the way that we do this is with samples from p theta, we can compute like an unbiased estimate of the squared error loss by subtracting off like a variance correction roughly. And through this sort of importance weighting view, right, that bias correction is also differentiable and it allows you to still get unbiased gradients. Yeah, and then so that and then some additional level grease in getting yeah, low variance control variance and further variance reduction for this KL term.
Isn't this very closely related to reinforce?
Yeah. I mean, this is everything but the very last line is reinforce. So reinforce policy gradient and score-based gradient estimates. I think of as largely synonyms of one another. Yeah. Yeah, it's good to make that connection explicit.
But this is also known to be like high variance estimate.
Yeah.
It's in the why people go to other estimators of optimization procedures for
IL, this was sort of like the original one of the early IL ways of updating policy, right? And, but it's known to be high variance. I don't know.
Yeah. I mean, I guess it's sort of a question of, is it low variance enough for your setting that you can do something useful with it? And yeah, I mean, I think the main sort of generic hammer for gradient estimation with generative models would be a reparameterization gradient. But yeah, I mean, this has limitations, particularly if you want to apply this in a setting where these H's are like non-differentiable. So if you have like an indicator, right, your options are limited. Yeah, so going back to this example I started with at the start. I guess I sort of said this in words a little bit earlier on, but we consider the starting point of this 15 million parameter diffusion generative model Genie2, and consider as statistics on the order of 1,000 bivariate quantiles of the secondary structure distribution, and then target for calibration at the empirical quantiles of these Cath domains. And then I guess a technical detail in this is, so I guess that this Genie2 model is actually initially developed in discrete time DDPM framework with 1,000 steps, but to speed it up, we move it into an SDE framework for these experiments. But even that doesn't really introduce problems computationally for computing these log density ingredients. So right, we can still compute this log p theta x as a Gersonov derivative relative to a static base measure. And here you can see in practice what the evolution of samples look like with this procedure. It's certainly far from perfect. I mean, looking at the sort of end on the top, we're not aligning exactly with this target, but I would say I'm quite satisfied with how much closer we get. So I guess one reason why I think this is significant is that with this hyperparameter, the amount of noise that we add at each step, the empirical results in the paper that introduces Genie2 that I mean, things keep marching forward, but at the time we're really quite empirical, impressive with good designability results based on these AlphaFold self-consistency tests for backbone generation quality. Where if you look at the fraction of design samples when you produce samples from the thing that actually should match your data distribution that you're fitting to, most of what comes out are design failures. And I mean, this isn't so surprising maybe because this is also true of many natural proteins. They don't hold up to these stringent structural prediction-based designability tests. But you do in fact get this when you reduce the amount of noise. So that's this sigma 0.5. We have very few failing designs, but with this huge shift away from these reference structures. But with these two variations of our method, we're able to really shift forward this Pareto frontier, getting both high designability with much smaller divergence from this reference data. And I suppose I mentioned this already before, but again, all you need to do is find a way to compute log likelihoods of your generations to apply this approach. So I mean, with the same exact code, we're able to do this for mass generative models. So examples in the paper on top of this ESM3 model for generating backbones, as well as normalizing flows in large language models. Yeah, and any other questions on this, or I'll shift on. Yeah. So I guess in the LM case, yeah. So the case we look at there is prompting this 9 billion parameter Gemma model from Google to generate like children's stories, like just a few sentences long in the style of, yeah, this sort of canonical test case for large language models. And look at like when we prompt like once upon a time there was like a doctor or a lawyer, we check what fraction of the generations have a male versus female like character name, or you can imagine wanting that to be roughly at parity if you're generating children's stories at least. And yeah, so we see, can we tilt this back to parity? So I think in practice, this is, I mean, for many problems, right, what we're accomplishing here could be combined through a combination of, right, using pseudo-random numbers to generate conditioning information to put into a prompt, and that would maybe be the most straightforward way to accomplish this with a large language model. But yeah, I mean, when you want this sort of parity to be baked into the weights directly, yeah, this is a strategy that we found works. Yeah, and in that case, I think actually because of this issue of high variance of the gradient estimates, or the variance of the gradient estimates in the LM case, because there are no latent variables that additionally add noise, is very stable. So right, with this 9 billion parameter model, we did this training on like one H100 GPU for a day or so, and yeah, it converges in only that time frame. Yeah, so next I'll move on to this yeah, earlier stage application. So this is, yeah, again, preliminary work that I think is particularly relevant to some folks here. But as sort of context for others, right, with understanding proteins and providing like scoring rules to incorporate in a design pipeline, molecular simulations have the promise of being quite useful for predicting molecular properties from samples from an underlying Boltzmann ensemble. All right, so like in this case, this is an example of what one of these simulations looks like, just pulled from the yeah, D. Isha research like website. Yeah, where you can see we're trying to simulate the like what the real motion of all of the atoms in the system looks like across time. And these approaches say there are two main algorithmic components: an energy function and a sampling method. And the main challenges to practicality come to limitations of these approaches. So in the choice of energy function, this can be difficult to tune and lack the full expressivity of what we would expect if we were to build up direct from quantum mechanics. And then the sampling yeah, is done through simulating a long Markov chain, which can be computationally expensive, particularly as one tries to resolve expressivity issues in the first stage. So a reasonable, yeah, more than reasonable, I think, idea for getting around these issues is to try to approximate such ensembles with a generative model, which probably in this crowd needs no introductions. This is something that Simon was involved in pioneering. Roughly the motivations here is that you can replace this restrictive energy function with an expressive neural network. So to get around these first issues, and then replace your Markov chain with a direct sampling mechanism to avoid that computational cost. There are a number of technical challenges for getting this to work well. But one of the challenges is yeah, that we fundamentally don't actually have ground truth samples to fit these generative models too, right? So this is the input to, yeah, I mean, the first stages of training for any model of language or of images or video or example samples of quite realistic, yeah, samples from the target distribution. Instead, we often have ground truth data from experiments in the form of ensemble averages, right? Things that we could express as the expected value of some statistic. And what we see is that, like, when you look at existing emulators of these Boltzmann ensembles, they're not consistent with thermodynamic measurements that get at these ensemble averages. So as a sensible question to ask is can we apply this sort of framework in this setting for specifically so far we've considered the case of protein folding energies. So right, with proteins you can think of as existing in equilibrium or for many small proteins at least between an unfolded state and a folded state. Right, and our goal is to have a neural network model that we put in some random noise and it produces samples, and we consider some of them are folded and some of them are going to be unfolded. And right, what we to map the raw measurements that we can get as folding energies onto this framework, right? These the measurements are measures of like a scaling of the log ratio of the probabilities of being in each of these states, right? So each of x is going to be 0 in the unfolded state and 1 in the folded state. And right, such measurements are possible to collect in very high throughput. So specifically, like we consider data from this cDNA display assay, and
Sorry, Brian, I think there's a problem with it. You check quickly.
Oh, yeah, thanks for bringing that up. Let me exit out of my slides. Yeah, so it says that I'm still connected.
It's the Zoom, because it's like you jump out of the Zoom.
There's no.
Yeah, I have disconnected from the Zoom. Maybe I can rejoin it.
Yeah.
Sorry, just a moment. Hopefully not too long ago. Okay. Okay. Is this working again? Great. We are back. So and for this week, we consider building on the setup for this biomolecular emulator model called BioEmu from Sarah Lewis and Frank Noe and that whole group at Microsoft that consider this the same exact problem. So here's looking first at an initial set of weights where we can see there's some correlation, but really not very strong in the alignment of an implied prediction of the folding energy with these experimental measurements. The only, I think, remotely closely related baseline for this task is what's proposed in that paper. We, in our hands, we're unable to get it to further reduce this calibration error from running. It can converges quite quickly, but to something without actually this improved correlation. And there are, I think, a number of reasons for this that I won't get into. But with the CGM relaxed approach, we find we're able to achieve like a much stronger correlation with these experimental measurements. Again, this is only on a very small set for now, and yeah, a large part of our initial exploration has been at a quite small computational scale. So all of this is fitting on a single GPU for several hours.
Is this test time? I guess so. You calibrate on a subset and then you test on a different subset and you get improved.
Yeah. So then this is the last slide I have on this is precisely that case of seeing do we actually get an improved agreement out of sample, right? So yeah, I mean, an additional bit of context setting the stage for where I think these methods will be useful. In the case where you really just have an unconditional model and are looking to achieve this calibration, just producing many samples and reweighting them, or if that's computationally inefficient, using guidance strategies like Simon has also been working on, I think are a very sensible solution, but there's no direct hope that will give you direct generalization to cases where you haven't actually already obtained measurements for which you would be able to do this sort of inference time calibration too. So this extrapolation setting where we're looking a correlation on unobserved on data that we haven't trained on, I think is really where these approaches might be most impactful longer term. And you can see in these preliminary results, the correlation still is very far from perfect, but quite significantly improved still. Absolutely. I would say a lot of this work is really still quite in flux. So some caveats, but and I think these first results I think are pretty promising. So to conclude, shown some new methods for calibrating generative models to distributional constraints in protein design. These are able to increase the match to cath, increasing diversity without degrading quality. And then in this sort of newer application to ensemble prediction, we're able to move towards calibrating a Boltzmann emulator model to better agree with experimental observables. Primary reference for this work is this paper, Calibrating Generative Models in the Archive, with a lot of the legwork done by these fantastic graduate students at Stanford. And with that, I'm happy to take any questions.
Questions for Brian? Bertha? The generalization based off of the end user group. Is there any theoretical reason to expect the reward to be better generalizing than the other one or less?
None that I am really aware of. I mean,
In practice, there is a difference in generalization probably between the two kinds.
So I guess in practice, specifically on top of this BioEmu model that we were calibrating, I mean, we found this reward approach through the maximum entropy characterization to not work so well. And I think this is, here, so I mentioned that there's a main difference practically is that you have this hyperparameter for the relax method. And we found that with the reward-based approach, we often will have some shift towards satisfying the constraint, but not move nearly far enough. Whereas by sort of really far upweighting the size of this violation penalty, we're able to trade off between moving farther from the base model and satisfying the constraint. So in principle, if we were able to do the optimization perfectly in a large model class, they should be the same. But I think the error from optimization is really quite significant. So in practice, so far in this case, it's seeming that this relaxed strategy works better.
Can you clarify again how this isn't really expensive to do? Because all of these are diffusion models, right? And I thought that the likelihood we need to sum over every single denoising step in order to get the final likelihood. And this to me sounds really expensive, but but in practice it's not a problem. So can you elaborate?
Oh, I mean, there's a reason that this first plot was only 5 data points. So there is definitely computational expense that I think is higher for the diffusion models compared to the LLMs for the same scale of model size because of I mean this trade-off of noise to but it's I mean I think I mean I guess there's I think improving efficiency is definitely a problem, but I mean, if you care about a distributional property, I don't know if there's a sensible way to think about that doesn't involve sampling from your model. And the step of additionally computing gradients on top will add maybe a factor of 2 or 3 if you're using checkpointing. Yeah.
I mean, one thing that you could consider is if it's very expensive is to basically, I guess this is the big data set, this mega mutation data set is to basically compute the expectations or the covariance under the model and then project and then align, do a calibration on a sort of a subset of the mutants that are representative for the whole data set. So basically and then hope, because there will likely be some redundancies and that will be equally informative with respect to the base distribution.
Yeah.
So you could make a selection sort of way, instead of making it more efficient, you could be smart about what data points that will give you the most information for calibration.
Yeah. I think that makes a lot of sense. I mean, one thing that I think is most unclear in this space is it's computationally complicated enough that just naively saying like, oh, let's 10x our computation and hope that like the first thing we try works. So I think that there's some maybe more complicated trade-off between, right, like, I mean, there are many other hyperparameters, right, that I haven't explicitly described related to like learning rates and the batch sizes that you use for these estimators. But yeah, I mean, like how increasing the batch size to reduce individual gradient estimates versus trading off the number of samples if you care about generalization, I think is I'm sure that there's a balance that isn't like all the way swung to one or the other. But I don't know if there's a way to get at it without empirically sort of building scaling laws, so to speak.
Any other questions for? I have one. So you hinted at the beginning. So like Debs had asked about like if you have these high dimensional targets, right? These statistics that you want to optimize for. Then might be conflict between them, right? The functions, the proxies that you have for these statistics, they might be imperfect, right? They might have a systematic or random error. Like the H's are often not like perfect models, right? In these cases, where you have like, for instance, this H star you have folding and unfolding with it, like requires you to have like a clear delineation of what is folded and what is unfolded.
Sure, yeah.
Right? So this would be the isochromator surface, like that you rarely have access to for an arbitrary protein. Right? So how sensitive do you expect this to be towards like the systematic and random errors in this statistic model you have?
Yeah. It's a great question. I don't have a good, I mean, specifically in this like Boltzmann ensemble calibration, I don't have a great answer to that.
And so if the H's are somehow conflicting, right, they could also be.
Yeah. So in that case, I mentioned the conditions for this reward approach being well defined. So the main condition is that right, this H star be in the relative interior of the collection of these H's that you have. So if they're directly in conflict, then that's off the table. The maximum entropy solution is not well defined. But I mean, you could still use the relaxed approach and then have something that meets in the middle for the ones that can't be satisfied. Yeah, so I mean, I guess for many of the cases, I mean, all the cases in our paper, we look at sort of trade-offs like this between some notion of distance from the calibration constraint and deviation from the base model. And yeah, I mean, I guess the main Pareto frontier that we've explored that I haven't been showing is to do with this hyperparameter lambda. But I think there are a lot of things that sort of fit on this.
Yeah, any final questions? Otherwise, we'll wrap it up by saying thank you, Brian. Out in front here.